Hello student, welcome to my channel The Learn Physics. I have already uploaded the one-shot video of ncert chapter 1, 2, 3, 4 and 5. Now today I will be discussing the one-shot video of ncert chapter 6, that is Electromagnetic Induction. Now today's discussions are Introduction of Electromagnetic Induction, Faraday's experiment, magnetic flux, law of EMI, and various types of discussion on these laws, Lenz's law and conservation of energy, motional EMF due to rotation of a conductor, energy consideration on EMI, inductance, that is self and mutual inductance, and AC generator, and finally all types of numericals of ncert relating to these topics. So let's start. Scientists Ørsted discovered that when a current passes through a conductor, magnetic field is produced around it. This phenomenon is known as magnetic effect of current. When reverse is true, that is, magnetic field can produce current. In this field, scientist Faraday successfully proved it, that a changing magnetic field produces current. Now changing magnetic field produces current. This is the EMI. What is EMI? When a magnetic field changes in a coil, current is produced. This phenomenon is known as electromagnetic induction. Now Faraday's experiment. In Faraday's experiment, the key word is oppose. That is, the current opposes the cause by which it is produced. That is, EMI always opposes the cause. Okay, look at this. N pole moving towards the coil. If N pole moving towards the coil, the magnetic field in this coil, look at this, the magnetic field in this coil increases, and this is the cross magnetic field. When the north pole moves along this direction, the strength of the magnetic field increases, so cross increases. Okay, look at this. Here the EMF induced, the induced EMF always opposes the cause, that is, it produces anti-clockwise. So current in the coil be anti-clockwise. When look at this, the inward magnetic field in the coil increases, the anti-clockwise current is produced. When north pole moving towards the coil, anti-clockwise current is produced. Okay, look at this. When north pole moves away from the coil, so north pole moves away from the coil, this current flow in such a way that S pole produced in the coil. S pole produced in the coil means it is a clockwise current. So look at this. When N pole moves away from the coil, look at this. The cross magnetic field decreases, and this is the clockwise current. Okay, understood? Look at this. Here cross magnetic field decreases. When cross magnetic field decreases, current induced in it is clockwise. Okay, understood? So there are two cases. Look at this. Here cross decreases, clockwise current. N pole moves away from it, clockwise current. Okay. Now next, when S pole moving towards the coil, the induced current opposes the movement of this pole. So it must induce south pole. Which produces south pole? Now clockwise current produces south pole. So induced current must be clockwise. So look at this. This is the clockwise. Okay, this is the clockwise. Now when S pole moves towards the coil, here dot magnetic field, that is outward magnetic field, increases. So look at this. When outward magnetic field increases, the clockwise current is induced. Okay? When S pole moves away from the coil, the current induced in this coil in such a way that it opposes the movement of S pole. So as it moves away, so here current induced in such a way that it attracts south pole. So it must be anti-clockwise current. So look at this here, anti-clockwise current. Okay, here anti-clockwise current, and here look at this, dot field decreases. Okay, so now in context of magnetic field, look at this, cross increases, anti-clockwise, dot decreases, anti-clockwise, cross decreases, clockwise, dot increases, clockwise. Okay, no problem. Look at this, cross increases, anti-clockwise, cross decreases, clockwise, dot increases, clockwise, dot decreases, anti-clockwise. The magnitude of induced current in the coil depends on number one, the strength of the pole, that is the magnetic field. Okay, number two, area of the coil. Number three, the number of turn in the coil. This is the number of turn in the coil. And number four, the rapidity of movement, that is time during which the movement takes place. So this is the time t. And finally, the direction of motion with respect to the axis of the coil, that is angle of movement. So this is the theta. So there are 5 factors on which induced current depends. This is the strength of magnetic field, this is the area of the coil, this is the number of turn in the coil, this is the time during which its movement takes place, and angle, that is direction of movement of the magnet. Okay. Now some example related to it. This is the inward magnetic field. Now this is a closed flexible wire. If this wire stretched, now the wire stretched in such a way that it is made circular. When it is made circular, its area increases. As area increases, so cross in this area increases. Now cross increases, that means N pole moving towards the coil. So anti-clockwise current is produced. So direction of current is this direction. Okay. Now when it becomes circular, the current this direction. So the direction of current anti-clockwise is, that is A, D, C, B, A direction. Okay. Now next. Now this is circular flexible ring is a normal outward magnetic field, that is dot magnetic field. Now force applied at the point C and D, so it compresses. So look at this, C point goes to C dash, A point goes to A dash. So the loop becomes this way. Now what is the direction of current? Look at this, for a given perimeter, area of circle is maximum. When it is formed in the shape of an ellipse, its area is less. As area decreases, so number of dots in it decreases. That is, south pole moves away from the coil. So current induced in it is anti-clockwise. That is, direction of current becomes, look at this direction. That is A dash, D dash, C dash, B dash. Okay, understood? Next. Now magnetic flux. The magnetic flux in an area element A vector is the dot product of magnetic field vector in this area element and area vector. So phi equal to B vector dot A vector, that is B A cos theta, where theta is the angle between B vector and A vector. We know the area vector is always normal to the plane of it. So look at this, look at this. Suppose this is the, look at this is the B vector. Okay. Now, if area vector A is this, so look at this. Here phi becomes B into A, because here A vector and B vector are parallel. Okay. Now look at this. If area vector is this, so here look at this, A vector and B vector is perpendicular. So here phi equal to 0. Now finally look at this. If area like this, okay, so look at this. This is the area vector. So area vector makes an angle theta with the B vector. So in this case, the flux becomes B A cos theta. Okay, the SI unit of flux is Weber and cbse unit is Maxwell. Okay, and 1 Weber is equal to 10 to the power 8 Maxwell. And its dimension, look at this, the dimension of flux is dimension of magnetic field into dimension of area. Now, dimension of magnetic field mt minus 2a minus 1 and dimension of area is L square. So, dimension of flux m L square t minus 2a minus 1. So, its dimension is just like energy by current. Okay, next. Look at this. This is the N pole. When the magnet is stationary, the number of lines of force crossing in this coil is constant. So no EMF is induced. When the north pole moves towards the coil or away from the coil, the number of lines of force within the coil increase or decrease. When number of lines of force in the coil increase or decrease, that is flux changes, then EMF induced. This is the main principle. So whenever flux changes in a coil, EMF is induced. Okay. Now laws of electromagnetic induction. Now first law. Whenever flux changes in a coil, EMF induced in it. That is E proportionate d phi. Okay. Now second law. Second law, the magnitude of induced EMF is the time rate of change of magnetic flux linked in the coil. So look at this, E proportionate d phi by dt. Now third law. Third law is called Lenz's law. The induced EMF always opposes the cause by which it is produced. So look at this. So E equal to minus d phi by dt. If number of turn in the coil be capital N, so look at this, E equal to minus n d phi by dt. Okay. Now explanation of electromagnetic induction. We know phi equal to, this is the B A cos theta. So look at this, E equal to minus n, this is the d dt of B A cos theta. Okay. First of all, average induced EMF. Look at this, the average induced EMF, this is the n B A cos theta divided by t. If theta equal to 0 degree, that is magnetic field is normal to the plane of the coil. So look at this, E becomes minus n B A by t. So this is the average value of induced EMF. Now what is induced current? Now induced current, now average current minus n B A by t into R. What is charge? Now charge Q equal to I into T. So this is the minus NBA divided by R. So charge flowing in the coil is independent of time. This is the NBA by R. Okay. So look at this. The average induced EMF, This is the NBA by T. This is the current. Look at this. This is the current NBA by T divided by R. That is the resistance. And now look at this charge flowing in the coil. This is the minus NBA by R. That is independent of time. It also written as, look at this, delta phi by R. This is very important in context of EMI. Okay, and when B is the function of time. Now look at this. In this case, E equal to minus NA cos theta. This is the dB by dt. Okay. Now when magnetic field is the function of f of t and x, then EMF E equal to minus NA cos theta, and this is the del V by del T plus V into del V by del X. Okay, this is also important relation for EMI. Next, when area A changes, look at this, when area A changes, then look at this, E equal to minus N B cos theta. This is the dA by dt. Okay, and finally, when theta is the function of t, that is theta equal to omega t, then look at this, E equal to minus N d dt of B A cos omega t. So look at this, this is the minus NBA, this is the d dt of cos omega t. Now differentiation of cos omega t is the minus omega sin omega t. So this is the N B omega A sin omega t. This is known as AC current, and this term is known as peak value of AC, and E is the instantaneous EMF of AC. Okay. Now ncert 6.3. Now number of turn in a solenoid is 1500 per meter. Current changes from 2 ampere to 4 ampere in 0.1 second. Now we have to calculate EMF induced in this coil, which is placed normal to the axis of the coil. That is theta equal to 0 degree. Okay. Now first of all, we have to calculate magnetic field V1 and V2. So look at this, V2 minus V1, so this is the mu naught N, this is the I2 minus mu naught N I1. So look at this, mu naught N, this is the I2 minus I1. Okay, now look at this, I2 minus I1 2, so this is the 4 pi into 10 to the power minus 7, this is the 1500, and this is the 2. So look at this, this is the 3000 and 12,000. So this is the 12,000 into pi into 10 to the power minus 7. So this is the 12 pi into 10 to the power minus 4 Tesla. Okay. Now look at this, the induced EMF. Look at this, the induced EMF minus 12 pi into 10 to the power minus 4 into area. Look at this, area of the coil is 2.0 into 10 to the power minus 4 divided by time 0.1 second. Okay, this is the 1.2 pi into 10 to the power minus 6 volt. This is minus 1.2 pi microvolt. Okay, now ncert 6.6. Look at this, a circular coil of radius 8 centimeter rotates about its vertical diameter in a magnetic field 3.0 into 10 to the power minus 2 Tesla with angular velocity 50 radian per second. Okay, now we have to calculate the average value of induced EMF, maximum value of induced EMF, and average power dissipated. We know the instantaneous value of EMF E equal to E naught sin omega t. Look at this, the average value of sin omega t is 0. So average value of induced EMF is equal to 0. Now peak value of induced EMF. Peak value of induced EMF, this is the N, B, omega A. Okay? So look at this. This is the N equal to 20, B equal to 3.0 into 10 to the power minus 2. This is the 50 and into, look at this A. A equals to 64 pi into 10 to the power minus 4. Okay? So look at this. E naught equal to, this is the 30 into 10 into 64 pi into 10 to the power minus 4. Okay? So this is the 0.60 volt. Okay? Look at this. Resistance R equal to 10 ohm. So maximum current I makes equals to 0.6 by 10. So this is the 0.06 ampere. Now average power is the half of maximum power. So P average is equal to half. This is the E naught I max. Okay. So look at this. This is the 0.60 into 0.06 by 2. So this is the 0.018 watt. Okay. Now ncert 6.6. The area of a coil is side square, that is 0.12 square. Velocity 8 centimeter per second. The velocity of the square coil is 0.08 meter per second. The magnetic field decreases along the negative direction of x-axis. Therefore, del B by del x is the minus 10 to the power 3 Tesla per centimeter. That is 10 to the power minus 3 Tesla per meter. This is the negative side. And del B by del T, magnetic field decreases at this rate. We have to calculate the induced EMF and induced current, and resistance is given. Now look at this. Here magnetic field along the positive direction of x-axis. Now area, length along x-axis, breadth along y-axis. So it is also directed along z-axis. So B vector and A vector are parallel. So therefore E equal to minus A. So E equal to minus A. This is the del B by del T plus V into del B by del B. Because magnetic field both changes with time as well as changes with space. So look at this. E equal to minus A. A equal to 0.0144. Now del B by del T, look at this. Del B by del T equal to negative sine of, look at this, negative sine of 10 to the power minus 3. Plus, now velocity 0.08 into negative sine of, look at this, del B by del T 10 to the power minus 1. Okay? Now look at this. So this negative and negative, so positive. So this is the 0.0144 into, look at this, 10 to the power minus 3, and this is the 8 into 10 to the power minus 3. So this is the 9 into 10 to the power minus 3. Okay? So this is the 12.96 into 10 to the power minus 5. Okay? Now I equal to, look at this, E by R. Now E equal to 12.96 into 10 to the power minus 5 divided by 4.5 into 10 to the power minus 3. Okay? This equal to 2.88 into 10 to the power minus 2 ampere. Okay? The induced current I directed in such a way that it always increases the flux along the positive direction of z-axis. Okay? To calculate the magnetic field between the two pole pieces of a strong loudspeaker, a search coil of area 2 cm square, number of turn 25, introduced in it and quickly removed from here. The charge flowed in the galvanometer is 7.5 into 10 to the power minus 3 coulomb. We have to calculate this. Okay? Now look at this. We know the charge Q is independent of time delta phi divided by R. Now delta phi equal to NBA divided by R. Now B equal to, look at this, Q into R divided by N into A. Now put the value. Q equal to 7.5 into 10 to the power minus 5. So this is the 7.5 into 10 to the power minus 3. Resistance R equal to 0.5. Number of turn, this is the 25. And area of the coil, this is the 2 into 10 to the power minus 4. Now look at this and this. So this is the 10. Okay. Now this and this is the 3 and this is the 10. Now this and this cancel out. So look at this is the 1.5 divided by 2. Okay, this is the 0.75 Tesla is the magnetic field between the two pole pieces. Okay, now next. Now Lenz's law and conservation of energy. According to Lenz's law, when n pole of a magnet is brought towards a coil, anticlockwise current is induced in it. Now we consider, instead of anticlockwise current, clockwise current is induced in it. If clockwise current is induced in it, then here S pole induced here. So this induced S pole attracts N pole with more and more forces. So without any mechanical work, the velocity of incoming N pole increases. This violates the conservation of mechanical energy. So our assumption is wrong. Due to incoming North pole, the anticlockwise current is induced. Therefore, the Lenz's law does not violate the principle of conservation of mechanical energy. Okay? Now, motional EMF. Now to discuss motional EMF, first of all, Fleming's right hand rule. Look at this. If this is the direction of magnetic field, this is the motion of the conductor, then this represents the direction of induced current. So these two are the cause and this is the effect. Okay? Look at this, a rod of length moves perpendicular to its length with velocity v in a normal magnetic field. Distance traveled by PQ in time t is v into t. Now, if length of the rod is PQ, then area swept by PQ, this is the L into v into t. As motion of the conductor is perpendicular to the velocity and also perpendicular to the magnetic field, so flux linked with the PQ, this is phi equal to B L V into T. Therefore, induced EMF E equal to phi by T, so this is the BLV. Now, what is the direction of induced EMF? Look at this. From Fleming's right hand rule, look at this. This is the direction of magnetic field. This is the motion of the conductor. So, direction of flow along this. So, direction of induced EMF is this to this. So, the rod PQ behaves as a battery of EMF E equal to BLV, which sends current from P to Q. Now, if a resistance R is connected with PQ, then the current through R is E by capital R. So, this is the BLV divided by R. Understood? Now, the magnetic force experienced by PQ due to its motion, this is the F equal to BIN, where I is the current through PQ. This is the current I equal to BLV by R. So look at this. this is the B square L square V divided by R, force experienced by PQ. So direction movement along this direction and force along this direction. So work is done by external agent. Power required for this motion by an external source P equal to force into velocity. So this is the B square L square V square divided by R. Okay, understood? Now next. Now look at this numerical 6.4. A rectangular coil of length 8 cm and breadth 2 cm. It moves normal to the length with velocity 1 cm per second in a normal magnetic field B equal to 0.3 Tesla. We have to calculate the motional EMF. Now motional EMF in the first case, this is the BLV, this is the E1. Now what is B? B is the 0.3 Tesla, L equals to 8 into 10 to the power minus 2 and V equals to 1 into 10 to the power minus 2. So look at this, this is the 2.4 into 10 to the power minus 4 volt. Okay, now the time during which this voltage exists. So time taken to travel 2 cm. So time this T1 equals to 2 divided by V. So 2 cm divided by 1 cm per second. So this is the 2 seconds. Okay. Now when it moves normal to its depth. So EMF induced E2 equal to, look at this. This is the B LV. This equal to 0.3, L equals to 2 into 10 to the power minus 2 and this is the 1 into 10 to the power minus 2 volt. Okay. So look at this. This is the 0.6 volt. Okay. The time during which this voltage exists, T2 equal to, this is the length by speed. So this is the 8 by 1. So this is the 8 second. Okay. Understood? Now next. Now look at this. This is a horizontal wire of length 10 meter. Extend from west to east. It is falling with speed 5 meter per second. The horizontal component of Earth magnetic field is this. Find the induced EMF. Now induced EMF E equal to BLV. B equals to 0.3 into 10 to the power minus 4. L equals to 10 and this is the 5 volt. Okay. So look at this. This is the 15. So 15 into 10 to the power minus 4 volt. So this is the 1.5 millivolt. Now what is the direction of induced EMF? Look at this. Applying Fleming right hand rule. Look at this. This is the direction of magnetic field. This is the direction of falling. So this is the direction of induced EMF. So induced EMF directed from this direction. This wire acts as a battery of EMF E equal to 1.5 volt, as inside the battery current from negative terminal to positive terminal. So this is the higher potential and this is the lower potential. Mind it. Look at this. A jet plane moving with velocity 500 meter per second towards west. Length of the wings of the jet plane is 25 meter. The total magnetic field is given. Angle of dip inclination is also given. We have to calculate the potential difference at the two ends of the wing. Okay, at the jet plane moving towards west, that is horizontal direction. So it cuts the vertical component of magnetic field. Look at this vertical component of magnetic field. So this is the B sine I. Okay. Now what is the B? B is the 5 into 10 to the power minus 4 and this is the sine 30 degree. So look at this. This is the 2.5 into 10 to the power minus 4 Tesla. Now what is the EMF? EMF is the vertical component of magnetic field into length into velocity. So this is the 2.5 into 10 to the power minus 4. This is the 25 and this is the 500 volt. Okay. So look at this. This is the 3.125 volt. Okay. Now, motional EMF due to rotation of a conductor of length L. Suppose the conductor rotates with angular velocity omega in a uniform magnetic field. So, angular velocity of dx at a distance x from O is v equal to omega into x. Therefore, the motional EMF produced in dx is d equal to b into dx into v. V is the omega x. So, motional EMF produced due to length L is equal to integration of, look at this, 0 to L, this is the b omega x dx. Therefore, b omega integration of x dx from 0 to L. So, this is the b omega, this is the L square by 2. This is the expression of motional EMF due to rotation of the conductor of length L. Now, applying Fleming's right hand rule, the direction of motional EMF, look at this, this is the motion of the conductor, this is the magnetic field. So, the direction of induced EMF directed from A to O. Okay. So, the conductor acts as a battery of EMF E equal to B omega L square by 2. So, O is the higher potential and A is the lower potential. Understood? Now a numerical. ncert 6.5. A conductor of length 1.0 meter rotates with angular velocity 400 radian per second about its one end in a uniform magnetic field 0.5 Tesla. We have to calculate the EMF developed in it. Now look at this, here E equal to half B omega L square. Look at this, here half B is equal to 0.5 Tesla, omega equal to 400 and L equals to 1 square. So this is the 200 into 0.5, so this is the 100 volt is the EMF developed at it ends. If it is the crossed magnetic field, so this center, look at this center is the higher potential and this is the lower potential. Okay, understood? Now next, now self induction. When switch is on in a coil, the current increases from 0 value to its maximum value. So during increase of current, the magnetic field in this coil also increases. Therefore, flux linked in the coil also increases. As change of flux produces induced EMF, so here induced EMF is produced. This induced EMF opposes the cause by which it is produced. Cause is the increase of current, so more time required to get the maximum value of current. As induction produced in it due to current itself, that is why it is called self induction. Now the flux linked in the coil due to instantaneous current I is phi proportionate I. Therefore phi equal to Li, where L is called coefficient of self induction or self inductance. L is depends on number of turn in the coil, area of cross section of each turn and nature of material inside the coil. Now induced EMF E equal to minus d phi by dt. So look at this, this is the minus d dt of Li, therefore minus L di by dt. Okay, so look at this, if di by dt is equal to 1, then L equal to minus E. Okay, so look at this, the self inductance is numerically equal to induced EMF in the coil when rate of change of current in the coil be unity. Its unit is Henry. Its dimension m L square T minus 2 A minus 2. Okay. Now the definition of Henry. The self-inductance of a coil is said to be 1 Henry if 1 volt EMF is induced in it due to rate of change of current of 1 ampere per second. Okay, now energy stored due to increase of current from 0 value to maximum value I naught is U equal to half L I naught square. Now expression of self-inductance. Suppose total number of turns in this coil be capital N and length of the coil is small n. So number of turn per unit length is N by L. Okay. Again, the magnetic field produced in the coil due to instantaneous current I is given by B equal to mu naught Ni, that is mu naught Ni divided by L. Okay, so flux linked in the coil phi equal to NBA. So look at this, this is the mu naught N square AI divided by L. Now we know the flux linked in the coil due to instantaneous current I is equal to phi equal to Li. Therefore, this equal to this. Therefore, self-inductance L equal to mu naught N square A divided by L. Okay. Now, we have to express the energy density in terms of magnetic field B. We know the energy stored in a coil of inductance L due to increase of current from 0 to I naught is U equal to half L I naught square. Now L equal to mu naught N square A divided by L. So look at this, U equal to half mu naught N square A divided by L into I naught square. Okay. If small n be the number of turn per unit length, then small n can be replaced by half, this is the mu naught N square L square A I naught square divided by L. So look at this, this is the half mu naught N square I naught square into AL. U divided by AL, this equal to half, this is the mu naught square N square I naught square divided by mu naught. So this is the magnetic field. So this is the B square by 2 mu naught. Now look at this. This is the capital A, area of cross section of the coil. L be its length. So look at this, A into L is the volume of the coil. So energy by volume, that is energy density. So energy by volume, that is energy density U equal to, this is the B square by 2 mu naught is the energy density in the magnetic field. Okay. Now 6.8. The current in a coil decreases from 5.0 ampere to 0 ampere in 0.1 second. Due to this, the induced EMF is 200 volt. We have to calculate the self-inductance. We know the induced EMF E equal to minus L di by dt. Now look at this, E equal to 200 volt. Now look at the di equal to minus 5.0 and dt equals to 0.1. This is the 50L, okay, and this is the 200, therefore L equals to 4. Therefore self-inductance is 4 Henry. Okay. Look at this, the length of a solenoid 0.30 meter and its area of cross section 25 into 10 to the power minus 4 meter square. Number of turn in it is this. Now the current flow 2.5 ampere in it. Now suddenly the switch is off. We have to calculate the magnitude of back EMF induced in it. We know the induced EMF E equal to minus L di by dt. Again L equal to, this is the mu naught n square A divided by L. Put the value of L in here. Look at this. So E equal to minus mu naught n square A by L into di by dt. Look at this. Mu naught is the 4 pi into 10 to the power minus 7. N is the 500 turn. So look at this. This is the 500 square. Now A is the 25 into 10 to the power minus 4. Now current changes from 2.5 to 0. So di is negative. So this is the minus 2.5 and dt. Now dt equal to 10 to the power minus 3 and length of the solenoid is 0.3 meter. So look at this. This is the 0.3. Okay. Now look at this. This into 400. 100 into 10 to the power minus 3, so 10 to the power 5. So look at this, this is the pi into 10 to the power minus 2. This is the 25 into 2.5 divided by 0.3. So look at this, this is the 625 pi divided by 3 into 10 to the power minus 2 volt. This is the 6.5 volt is the magnitude of induced EMF or back EMF. Now mutual induction. When current changes in this smaller coil, EMF is induced in the larger coil. This phenomenon is known as mutual induction. Now the coil in which current changes is called primary coil and the coil in which EMF is induced is called secondary coil. Now look at this. The flux linked in the secondary coil due to instantaneous current I in the primary is phi proportionate I. So phi equal to M into I, where M is the mutual inductance between the two coils. It depends on number of turn in the primary coil, number of turn in the secondary coil and area of cross section of the smaller coil and material inside the primary coil. Okay. Now EMF induced in the secondary coil E equal to minus d phi by dt. So minus d, this is the mi divided by dt. So look at this, this is the m di by dt. Okay, negative side. If di by dt is equal to 1, then m equal to minus e. Okay, so mutual inductance between the two coils is numerically equal to the voltage induced in the secondary coil when rate of change of current in the primary coil be unity. Okay, its unit is Henry and dimension m L square T minus 2 A minus 2. Okay, the mutual inductance between the two coils is said to be 1 Henry if 1 volt EMF is induced in the secondary coil due to rate of change of current in the primary coil be unity. Okay. Now next, the energy stored in the secondary coil due to change of current from 0 to I naught is U equal to, this is the half m I naught square. Okay. Look at now derivation of mutual inductance between the two coils. Look at this. Suppose number of turn in the primary coil be N1 and its length is L. So number of turn per unit length N1 equal to, this is the N1 by L. The magnetic field produced due to instantaneous current I in the primary coil B equal to, this is the mu naught N1 I. Now flux linked in the secondary coil phi equal to, this is the N2 B into area of the smaller coil. So this is the A. Okay, this is the N2. Now this is the mu naught and this is the N1 by L into A into I. Okay, so this is the mu naught N1 into A by L into I is the flux linked in the secondary coil. Now we know the flux linked in the secondary coil due to instantaneous current I is phi equal to M into I. So look at this. So therefore Mi equal to, this is the mu naught N1 N2 A divided by L into I. Therefore mutual inductance capital M mu naught N1 N2 A divided by L. So look at this. The mutual inductance between the two coils depends on number of turn in the primary, number of turn in the secondary, area of cross section of the smaller coil and medium within the primary coil. Okay, look at this. Two concentric circular coil of radius R1 and R2. Here R1 less than R2. When I current passes through the outer coil, we have to calculate the mutual inductance between the two coils. Now magnetic field at the common center due to current I is equal to B equal to mu naught I divided by 2 R2. Okay. So flux in the inner coil phi equal to, look at this, this is the mu naught I 2 R2 into area of this coil. What is the area of this coil? This is the pi R1 square. Now we know phi equal to M into I. Phi equal to M into I. Therefore M equal to mu naught I pi R1 square by 2 R2 divided by I. Okay. So look at this. This is the mu naught pi R1 square by 2 R2 is the magnitude of mutual inductance between the two coils. Okay. Now look at this. This is the straight conductor carrying a current 50 ampere. This is a square coil of side 0.1 meter. We have to calculate the mutual inductance between these two and induced EMF when x equals to 0.2 meter. Okay. Suppose a strip of width dy at a distance y from the straight conductor. Now magnetic field at a distance y B equals to, this is the mu naught I divided by 2 pi y. Okay. So the flux in this coil d phi equal to, this is the B into A. Now this is the B equal to mu naught I divided by 2 pi y and area of this strip is A into dy. So flux phi equal to integration of the lower limit is x and upper limit is x plus a. Look at this. This is the x and from this to this is x plus a. So this is the x and this is the x plus a, and look at this. This is the mu naught I divided by 2 pi into a and here dy by y. Now look at this. This is the mu naught I a by 2 pi and this is the ln y and here lower limit x and upper limit a plus x. So look at this. This is the mu naught I a divided by 2 pi and this is the ln a plus x divided by x. Okay, we know phi equal to m into I. So look at this, mi is equal to here mu naught I a divided by 2 pi into ln a plus x by x. Okay, now I cancel out, therefore capital M equal to mu naught a by 2 pi, and this is the ln a plus x by x is the magnitude of mutual inductance between this and this. Okay, now put the value of, look at this, here m equal to, this is the 4 pi into 10 to the power minus 7, a equal to 0.1 meter, so this is the 0.1, and this is the 2 pi, so this is the 2, and ln, look at this, x equals to 0.2 and the a equal to 0.1, so this is the ln 3. Okay, so mutual inductance is 2 into 10 to the power minus 8 ln 3. Okay, now magnitude of induced EMF. Look at this, this conductor is considered as a straight conductor. The EMF induced is equal to BLV. Now look at this, B equal to mu naught I divided by 2 pi x. A is the L and V is the velocity. Now look at this, is the 4 pi into 10 to the power minus 7, I equal to 50 ampere, and this is the 2 pi, look at this, x equals to 0.2 meter, so this is the 0.2 meter, a length of the side, so this is the 0.1, and velocity is equal to 10 meter per second, so this is the 10 meter per second. So finally the magnitude of induced EMF is equal to this volt. Now this equal to 1. Okay, now look at this, and this is the 2, this and this is the 10. So look at this, is the 5 into 10 to the power minus 5 volt is the induced EMF. Now we have to express the relation between changing magnetic field and electric field. Suppose here changing magnetic field becomes dB by dt. We know from Faraday's law of electromagnetic induction, E equal to minus d phi by dt. So look at this, E equal to minus a dB by dt. The EMF E can be expressed as the line integral of E vector dot dl vector. So E vector dot dl vector equal to minus a dB by dt. Now we have to calculate the electric field at a distance r from center of this magnetic field. So here look at this, the electric field in this circular region is directed tangent to the path. So look at this, E vector dot dl vector, so this is the E into 2 pi r, this is the cos 0 degree, and this is the A means this is the pi r square, and this is the dB by dt. So look at this, E equal to pi cancel out, this is the r square by 2r into dB by dt, magnitude of electric field at this circumference. Okay, now we have to calculate magnetic field on the surface of the circular region. So in the surface of the circular region, look at this, the electric field E becomes, look at this, smaller becomes capital R. So this is the r square by 2r, and this is the dB by dt. Okay, so this is the r by 2 into dB by dt. Okay, so here changing magnetic field produces electric field of magnitude r by 2 into rate of change of magnetic field with respect to time. Now inside at any point, look, this field becomes E equal to r by 2, and this is the dB by dt. So the graph becomes, look at this, this is the E and this is the R. So from this to this region, this is increases and this is the decreases. Here E proportionate R and here E proportionate 1 by R. Okay, understood? Now a numerical. Now look at this. This is magnetic field B exists in this region. This is circular coil of radius R, mass M, free rotate about this. We have to calculate angular velocity. When magnetic field changes from B0 to 0. So look at this, there is a changing magnetic field. The changing magnetic field is B0 by T. Now we have to calculate the angular velocity of it. As magnetic field changes from B0 to 0 in time t, so change of magnetic field is B0 by T. Due to this changing magnetic field, the electric field is produced. If E be the magnitude of electric field, now applying formula, the line integral E vector dot dl vector is equal to A into dB by dt. Now look at this, here E into, look at this, dl is the 2 pi r, so this is the 2 pi r, this is the cos 0 degree and A is the area of this region, so this is the pi square into B0 by T. Okay, so look at this, E into 2 pi r is equal to pi square B0 by T. Now look at this, the total charge in this ring is equal to length of the ring into lambda, so charge is equal to this. So force F equal to, this is the Q into E. Okay, so Q is the 2 pi r lambda into E. Okay, now look at this, here E into 2 pi r, so look at this, here F becomes 2 pi, look at this, F equals to 2 pi r lambda E equal to, this is the lambda pi square, this is the B0 by T. Now due to this force, the torque experienced by the coil is F into R. Now this torque is equal to I into alpha. Now I into alpha, look at this, I into alpha equal to F into R. So look at this, this is the half m r square, this is the alpha. Alpha means rate of change of angular velocity, so this is the omega by T and this is the F. What is F? F is this, so this is the lambda pi square B0 by T into R. Okay, now look at this T and this T cancel out. So look at this, omega equal to, so omega equal to pi square and lambda B0 divided by, look at this 1 r and r cancel out, so this is the 2 and this is the mr, is the angular velocity of rotation of this circular ring. Okay, now eddy current. When a metallic plate is placed in a changing magnetic field, then EMF induced in it. This EMF produces current in this metallic plate in various paths. This current is called eddy current as discovered by scientist Foucault. This eddy current produces heating effect. So this heating effect dissipates some electrical energy, so it is undesirable. So eddy current can be reduced by cutting slot. Look at this. This is the metallic plate. If slots are cut in this metallic plate, so path of eddy current reduces and eddy current decreases. In a transformer, the laminated iron core is used to reduce eddy current. Look at this. Suppose this is the N pole, this is the S pole. A pendulum oscillates between this. So magnetic flux changes in this plate, so eddy current induced it. As this current always opposes the cause is the its oscillation, so the eddy current stops its oscillation. Okay, so eddy current used to convert a moving coil galvanometer into a deadbeat galvanometer. Okay, now use of eddy current. Magnetic braking of train. A strong electromagnet placed above the rails. So when electromagnet activated, the eddy current produced, which opposes the cause and stops the train without any mechanical jerking. Next, electromagnetic damping. Few galvanometers have fixed core with non-magnetic metallic substance. When this galvanometer oscillates, the eddy current produces in it, which opposes the motion of the pendulum, okay, and stops quickly at the equilibrium position. Induction furnace. High frequency AC current pass through it, so eddy current induces in the furnace and produces high temperature. And finally, eddy current is used to electric power meter. Okay, now AC generator. First of all, definition. It is a device which converts mechanical energy into electrical energy is called AC generator. Now, principle. When a rectangular coil rotates in a magnetic field about an axis normal to the field, then EMF is induced. Now, components. Field magnet. These are the two poles of a strong electromagnet. The armature coil rotated in this magnetic field about an axis normal to the magnetic field. Now armature coil. Look at this, PQRS is the armature coil. This coil is rotates about the axis which is perpendicular to the magnetic field with angular velocity omega. Now next, slip rings. Slip rings are also rotates with the armature coil and they are in contact with the brass B1 and B2. And B1 and B2 are in contact with the slip ring S1, S2 and external circuit. And this external circuit produces EMF, is the output in which the EMF E equal to E naught sin omega t, that is the AC voltage is obtained. Look at this, this is the armature coil. So first of all, the plane of the coil is made normal to the magnetic field. Then it starts rotating with angular velocity omega. Therefore, in time t, the angle of rotation theta equal to omega into t. If n be the number of turns in the armature coil and A be the area of the coil, now the instantaneous flux linked in the coil, this is the N, B, A cos theta, where B is the strength of magnetic field. Now here N, B, A, this is the cos omega t. Now induced EMF equal to minus d phi by dt. So look at this, this is the N, B, A, omega sin omega t. Okay, so look at this, this is the E equal to E naught sin omega t is the magnitude of induced EMF, where E naught is the N, B, omega A is the peak value of induced EMF, and this is the instantaneous value of induced EMF. The peak value of EMF depends only on strength of magnetic field, because omega is constant, number of turn and area of the coil must remain constant to make it rotates 50 per second. Okay. Many thanks for watching this video. This video will be beneficial for you for your preparation in cbse, neet, main and advanced. Please like, share and comment on this. If you are new, don't forget to subscribe my channel.